Hello everyone, my name is Mohammad Aminul Islam. I am a postdoc in Oklahoma State University. Today I am going to talk about a computational modeling approach in the gut-bone axis and implications of butyrate treatment on osteoimmunology. First, I would like to acknowledge the co-authors for this work. Carly Cook is a master's student in our lab. Dr. Smith is our collaborator from Department of Nutritional Science, and Dr. Ford Forsyth is my postdoc advisor. So let's start with the background. Poor bone health is common and costly. In USA, each year, 1.5 million people suffer fractures from osteoporosis. 500,000 of them are hospitalized, and 180,000 people are placed permanently in the nursing home. According to the report from National Osteoporosis Foundation, 10 million Americans live with osteoporosis. 44 million Americans have poor bone mass, and it costs annually more than $19 billion. On top of that, the poor bone health becomes more prominent after the age of 50. 1 in every 3 women and 1 in every 5 men over the age of 50 will be affected by osteoporosis in their lifetime. So it is a huge problem, and one of the alternatives to prevent this is the use of dietary supplement. According to a report from Consumer Survey on dietary supplements, percentage of US adults taking dietary supplements increased from 65% to 75%, which is a 10% increase over the last decade. So dietary supplement is an alternative in the prevention and treatment of bone disease. And today I'm going to talk about one of the dietary supplements, which is butyrate. Butyrate is a short-chain fatty acid produced by the fermentation of the dietary fiber by gut microbiota. Chemically, it has 4 carbon chains followed by a carboxylic group, and we can increase butyrate in our body by consuming food that contains resistant starch, prebiotic fiber, and butyric acid-rich food. We can also take probiotic to increase butyrate-producing microorganisms, and then they will produce more butyrate in our body. So butyrate is produced in the intestine, but somehow it migrates all the way to the bone and contribute to the bone formation. Actually, butyrate interact with the immune cells, and their interactions with the immune cells contribute to the maintenance of bone health. So butyrate can be a possible treatment for different bone diseases such as osteoporosis, osteoarthritis, and so on. Now let's look into the mechanism of how butyrate is inducing bone formation. In the intestine, microbiota is producing the butyrate. The butyrate that is produced in the intestine then interact with the naive CD4 plus T cells, and their interactions cause the differentiation of naive CD4 plus T cells to regulatory T cells. Regulatory T cells are the central actor of negative feedback component of the immune system, and they suppress the inflammation. So this is a local effect of butyrate. The butyrate that is produced in the intestine and regulatory T cells then migrate from intestine to blood and from blood to bone compartment to exhibit their systemic effect. In the bone compartment, the regulatory T cells produces TGF-beta, which suppresses the inflammation. When the inflammation is suppressed, CD8 plus T cells then produce ONT10B. ONT10B promote the production of osteoblast, and when the production of osteoblast in bone is increased, they will contribute to more bone formation. So this is the mechanisms of butyrate inducing bone anabolism. However, the therapeutic benefit of butyrate in bone anabolism remain poorly understood. So our purpose here is to create a multi-compartment physiology-based pharmacokinetic model to track and quantify the effects of butyrate on regulatory T cells in the intestine, blood, and bone. Additionally, we connect ONT10B expression enhanced by the regulatory T cells to bone remodeling. We also validate our model with experimental observation. So in our model, we have three compartments: intestine, blood, and bone. We used set of ordinary differential equations to formulate our model. First, let's look into the intestine compartment. In the figure, each line represents the corresponding reaction rate, and the dotted line here represents that the component will take part in these reactions but will not be consumed by the reaction. In the intestine, we have considered a constant formation of butyrate, and butyrate can also excrete from the intestine. The butyrate in the intestine interact with the naive CD4 plus T cells in the intestine, and their interactions cause the differentiation of naive CD4 plus T cells to the regulatory T cells. Regulatory T cells in the intestine can also degrade. Finally, butyrate in the intestine absorbs into blood, and the regulatory T cells in the intestine also migrate from intestine to blood. In the blood, the source of butyrate is the absorbed butyrate from the intestine, and they can also excrete from the blood. The butyrate in the blood interact with the naive CD4 plus T cells in the blood, and their interactions cause the differentiation of naive CD4 plus T cells to regulatory T cells. Regulatory T cells in the blood can also degrade, and another source of regulatory T cells in the blood is the migrated regulatory T cells from the intestine. Finally, butyrate absorbs into bone, and regulatory T cells also migrate from blood to bone. In the bone compartment, the source of butyrate is the absorbed butyrate from the blood, and they can also excrete from bone. The butyrate in the bone interact with the naive CD4 plus T cells in the bone, and their interactions cause the differentiation of naive CD4 plus T cells to regulatory T cells. Another source of regulatory T cells in the bone is the migrated regulatory T cells from the blood. The regulatory T cells in the bone then produce TGF-beta, which suppress the inflammations. Then the TGF-beta promote the production of ONT10B, which enters into the bone remodeling cycle. ONT10B promote the productions of osteoblast and reduce the apoptosis. As a result, bone formation and bone volume increase in the bone compartment. Carly Cook, the master's student from our lab, is giving a talk on bone remodeling cycle in this conference in another sessions. So I put the details of that session in my iPoster, and if you are interested, you can listen to that. Now let's look into the simulated result and compare the simulated results with experimental observation. The top three figures shows the change in butyrate concentration in the intestine, blood, and bone from the homeostasis value. And the bottom two figures shows the distributions of regulatory T cells in the blood and bone compartment. Here, blue line represents the homeostasis value. That means when the intestine butyrate concentration is at homeostasis and delta B equals to 0 micromolar, we'll observe this blue line. Here, red bar represents the experimental results, and from experimental observations, we found out that when the intestine butyrate concentration is increased by 0.18 micromolar from homeostasis value, it will increase the amount of bone regulatory T cells from 42% to 48%, which is a 6% increase. So we set the intestine butyrate concentration to 0.18 micromolar increased from the homeostasis value, and we observe 5% increase of the regulatory T cells in the bone compartment, which is consistent with the experimental observation. Next, we looked into another experimental results where the butyrate concentration is reduced, which is similar to the pathological condition. In this experiment, they reduced the butyrate concentration using antibiotic. And their experimental results reveals that when the butyrate concentration in blood is reduced by minus 0.18 micromolar from homeostasis value, it will reduce the bone regulatory T cells by 5%. So we set the intestine butyrate concentration reductions to minus 0.11 micromolar from homeostasis value, which will recreate the blood butyrate concentration to minus 0.18 micromolar reductions similar to the experiment, and we observed 4.5% reductions in the bone regulatory T cells. This is also consistent with experimental observation. So we validate our model for both treatment conditions and pathological conditions, and now we are confident with our model. So we run the simulations for different change in the intestine butyrate concentration, both positive and negative directions, and run it over a longer time period to observe the dynamics of the bone regulatory T cells. These results will be helpful to develop new treatment where we can control the intestine butyrate concentration to modulate the anti-inflammatory regulatory T cells at different compartments. Next, we connect the dynamics of TGF-beta with our model. TGF-beta is produced from the bone regulatory T cells and they suppress the inflammation. But from experimental observations, we found out that for similar magnitude increase or decrease of the regulatory T cells will not yield similar magnitude increase or decrease of the TGF-beta. So we take two experimental data points, one for increase of the TGF-beta and one for decrease of the TGF-beta, and perform a simultaneous curve fitting to capture the dynamics of the TGF-beta in both directions. Again, from the experimental data, we got only one data point and don't know anything about the steady state value. So we assume the parameters and perform an iterative method where at each iterations we are evaluating the steady state value and then perform a simultaneous curve fitting to capture the dynamics of the TGF-beta. And the right side video is showing the simultaneous iterative curve fitting approach to evaluate the dynamics of the TGF-beta. So using the approach, we can evaluate the dynamics of TGF-beta for different butyrate concentrations. Here we assume that the ONT10B is directly correlated with the dynamics of TGF-beta and skip the part that ONT10B is produced from CD8 plus T cells. So once we know the dynamics of the TGF-beta for different butyrate concentration, using these assumptions, we can evaluate the dynamics of the ONT10B for different butyrate concentrations. And from the change of ONT10B, now we can evaluate the change in bone density. So this work gives us insight on the pharmacokinetics of butyrate regulatory T cells and their contributions to modulating the bone formation. This work also gives us understanding how butyrate modification could be used as possible treatment for different pathological conditions relating to bone, such as estrogen deficiency, vitamin D deficiency, and so on. This work is supported by NIH, and thank you for listening to me. If you have any questions, I'm open for discussion.